Hi, this is our for CS532. Here we are analyzing CPU versus GPU performance on different machine learning tasks. So, with the advancement of machine learning has increased the need for powerful computing hardware like GPUs, which excel in handling parallel computations. However, GPUs are often expensive and not always accessible, leading to a need for optimizing ML algorithms for CPUs as well. This project focuses on comparing the performance of GPUs and CPUs in various machine learning tasks. We aim to identify performance bottlenecks and analyze them across these platforms. As the demand for advanced machine applications grows, understanding the performance differences between GPUs and CPUs is essential. This knowledge will help us ensure the ML community continues to leverage the best available technologies for innovation. Here is our overall project design. We plan to analyze system differences in two different tasks, image classification and text classification, using various CNN and transformer models in PySpark. We also compare different metrics achieved when using a CPU and GPU. We also run different experiments by tuning the hyperparameters like number of epochs, batch size, etc. for various models and identify the bottlenecks when training and inferencing on a CPU versus GPU. We also develop a small-scale app for image classification task using PySpark streaming, and we divided the roles with Yash and Isaiah were tasked with obtaining results for image classification, while Abhishek and I were tasked with obtaining results for text classification modeling.
With regard to image classification, our goal was to compare the performances between multiple different models. And so our idea was to have a structure that could support the various model comparisons. So we chose the CNNs, convolutional neural networks, and transformers to be comparisons, looking at the difference between smaller models versus larger models. Utilizing pre-trained models, CNNs and transformers were fine-tuned on the CFAR10 dataset, and we utilized pre-trained models in order to save time. So here you can see some of the models that we used. As you can see, we weren't able to implement the largest models, but we still varied the model size between tiny and small, as you can see, and also base for some of the transformers.
For text classification tasks, we used BERT, which is a bidirectional encoder representation from transformer, which is a transform-based architecture that utilizes a bidirectional approach, enabling it to capture context from both directions of a sequence. It consists of multiple transformer encoder layers that process input data in parallel, allowing for deep contextual understanding. So we use three versions of BERT: Google BERT, Huawei BERT, and then Microsoft BERT. Each of them have the same architecture, but different sizes.
Okay, so for our image classification training task, we run on two systems: Linux TPU, which has a 2 CPU RAM of 12 and 15 GB CUDA, and with a Mac OS of 8 cores, 16 GB RAM, and 30 GB GPU. We use the same training parameters on the two environments to analyze the system performance and get the same baseline. There were issues with our CPU training due to memory consumption. Even with the smallest model, it either crashed or didn't move ahead. So we decided to instead analyze on different systems with GPUs. Also, I'd like to point out that we implemented the PyTorch distributor that supports multi-GPU training. However, since we didn't get the environment support, we restricted our training to a single GPU. For inferences, we ran on Linux TPU, Mac GPU, Mac CPU for getting analysis. The model evaluations were done on PySpark that utilizes distributed data operations, which is much faster than sequential processing. We also performed various PySpark transformations on the model inputs to get the aggregated results and for the visualizations. Finally, we fine-tuned the models on the different environments and we got same accuracies. So this gives us credibility for our system analysis. And on the PySpark streaming part, we used inferences pipeline that were already done and extended to develop an app that does streaming on real-time image classifications. We analyzed the results, finding the bottlenecks and potential improvements. Our analysis includes running the app on different systems and models using two Spark clusters.
Now I'll speak about the tests done in the NLP section of the presentation. So for the training part, we used a GPU from Google Colab. It's Tensor T4 GPU, which has a memory of 16 megabytes. And to run on CPU, we used a Mac CPU of 12 cores. Similar to the image classification, we use the same hyperparameters for CPU and GPU in order to compare them efficiently. Then for the inference part, we executed the distributed data inference to increase the evaluation speed on GPU. This was done by using PySpark. And here we analyze the difference between CPU and GPU performance by using two metrics. One is the time of execution and another is.
So this is our training analysis for the image classification models mentioned earlier. On the left side of the slide, we have two plots. These are scale normalized values for comparing the Mac and Linux GPU performances. Some of the important metrics were collected for our training, and these were the floss, the floating point operation per second, the runtime, the batches processed per second, and the steps taken per second. Note that in these plots, the floss for all the models on both the environments are same, which provides a good baseline as the model computations are same in both environments. The runtime for convex model is more than Mac GPU than Linux GPU, even though we have more GPUs in Mac. So after analyzing the frameworks and performing torch profile The reason turns out that during the backwards gradients calculation of convolution, the mental frame of operations is slower than CUDA. This is due to Apple's GPU compatibility and not the model. The transformer models have lower runtime for Mac GPU as expected. The batch processing and step processing is faster in Mac GPU for all the methods. However, convex model is faster for Linux GPU, even though there's more GPU for Macs. Again, that is due to the framework difference. Next, we compare the losses and accuracies. We have shown the model training for one epoch, and if we keep the performance aside, evaluation accuracies are very similar. For the losses, CUDA GPU is slightly better convergence than the metal GPU. And again, with profiling, we found this is due to the same issue as the convolution operation. We reach convergence on the environments when the models were trained on more epochs and fine-tuning the hyperparameters. Overall, we can see that the CUDA GPU is highly optimized and gives comparable train performance or even better with the metal GPU, even when it is half of the size of metal GPU.
Another interesting thing to note is the batch size compared to the average batch duration. As the batch size increases, it's expected that the average batch duration would also increase. But note that for the Linux CUDA, that GPU it barely increases the average batch duration as comparison to the both CPUs, where as the batch size increases, the average batch duration also significantly increases. And that's probably due to the time-saving effects of parallelization for the GPU. Also note that on the right side that the CPUs both performed took significantly longer in terms of duration than the GPU. However, the Mac CPU outperformed the Linux CPU.
Okay, so for our PySpark streaming, the architecture we developed is simple, involving two Spark clusters communication in a single direction pipeline. The images are being pushed at a constant rate, and we keep gradually increasing the images. So unlike our previous inference and training analysis, we get some different results here. We use 3 trained models on those 2 environments, Linux GPU and Mac GPU. And the Apple GPU is not compatible with the Spark cluster, so we exclude that. For our latency, we see the Mac CPU is performing much better because of more parallelized threads available in the Spark cluster. And only for the smaller convex model, the latency of the GPU gradually decreases. Similarly, for the throughput, the Mac CPU works better because of the highly parallelized cluster environment. And the CPU throughput is higher or similar to the GPU for each model. And similarly, for the smaller convex model, the throughput is gradually increasing once the overhead of transferring data from CPU to GPU is negated. We can conclude that for developing an app for real-time processing, having parallelization is equally or perhaps even more important than GPU.
In this slide, we are comparing the CPU and GPU on the basis of the duration, execution duration. Over here, we can clearly see there's a gradual increase in the execution duration as we increase the batch size, whereas on the GPU part, there's a slight decrease and then the graph goes constant. This is because GPU utilizes parallel execution. As we can clearly see that we have used very less batch sizes. This is because of the computational constraints, as it was taking a lot of time to compute on these results over CPU. Thus, we have kept the batch sizes less. In this slide, we are comparing the CPU and GPU on the basis of the accuracy. Here we can clearly see that there's not much of a difference of accuracy since while increasing the batch size. Thus, we can clearly infer from this slide that using GPU doesn't increase the accuracy of the model. It just decreases the execution time.
Now here we analyze the bottlenecks for both CPU and GPU. We analyzed it for 3 models, Roberta, Vision Transformer, and the convolution networks. As you can see for the GPU, for all 3 models, the bottleneck is the attend copy, which is basically the operator that moves the tensors from the CPU and GPU and vice versa. And for the CPU, we can see that the bottleneck is the add BMM, and the convolutional operators, as these are not optimized for the CPU, whereas they are very much optimized for the GPU. We can obviously see from the tables that the total time taken by the GPU is way lesser compared to the CPU. So here we reflect on our project in terms of the goals that we wanted to complete using this project. We compared different model architectures of different sizes to analyze performance on CPU and GPU, which we did achieve. We compared key metrics such as accuracy, latency, throughput for different tasks while training and inferencing, which again we achieved. We understood the different bottlenecks in a CPU and a GPU, and we also built a streaming process for images using PySpark, and also compared its performance on the CPU and GPU.
Okay, so due to the limitations of multi-core GPUs or CPU RAM availability, we couldn't analyze larger models that probably would give better results. Running experiments on systems with these resources, we could have performed faster inferences, save module variation time, analyze different model performances. For our PySpark streaming we have limitations on the development of the application itself. There are several improvements that we can do to the app. One of them is, instead of using the current architecture, which uses a JSON file, you use a DB. And the other one is a thread locking mechanism so that the clusters will communicate synchronously and give persistent loggings and accurate results.